So what's going to happen next is we're going to get just random graphs without anything labeled. And based on those random graphs, have to think about what the graph of the derivative would look like and what the graph of the second derivative would look like. So here is our first graph, and we had a quadratic equation. Okay? You can think about it numerically. If you took the derivative of a quadratic equation, you would get like 2x. It would be a straight line. Okay? This quadratic equation is also a negative because it's opening down. So you could also say, well, then I would get negative 2x. So my slope should be negative. So that gives us the general idea that I'm going to get a straight line going down. What does the first derivative tell us? The first derivative finds us critical points, and those critical points match up with maximums or minimums. So if on my original graph I have a maximum there, does it make sense that on my derivative graph I would have an x-intercept? One thing that I find really helpful with these questions is we were only given the red graph, right? On the red graph, you know you have a maximum. You could draw your first derivative, pick that point C, I don't know where it is exactly, and I know that that is a critical point because I have a maximum. I also know that my original graph goes up and then goes down. So if it's going up and then going down, is it F here? Yeah, F prime. That means in F prime, I would have had positive, then negative. Look on the blue graph. Do you see that your y values are positive on the left side and negative on the right side? So I knew this line was going down because I could tell that my parabola was normally a negative x squared parabola. And if I did just a random derivative of a negative x squared, I'd get negative 2x. There might be other numbers, doesn't matter. But a negative 2x would be a slope that goes down. So I knew that from that, but you can also see by taking the original graph and saying, if I was graphing this, I would have gotten my first derivative, and I would show where it's increasing and decreasing. And the increasing and decreasing is about the original graph, but the plus and the minus is about f prime. And so I can see my graph is positive here, negative here. There are no points of inflection on this parabola. If I had my number line for f double prime, I would have no numbers on there whatsoever. I can see that my original parabola, the whole thing is concave down. If the whole thing is concave down, how do we tell that from the second derivative? Second derivative has to be negative. Notice the line that they've drawn here, that all of the values are less than the x-axis. They had to make it negative somewhere. Okay? Also, whatever the slope of this line is, this slope was negative 2, then this line would be at negative 2. So we're doing a little bit of guessing because we don't know exactly what the actual equation is. We're just ballparking where the graph is. As long as you showed your f double prime as a horizontal straight line, because the derivative, the second derivative is the first derivative of the first derivative, and it has a constant slope because it's a straight line, makes that completely flat. This is probably the easiest because they gave us the original graph. If we move to the next one, It also gives us the original graph. And the next one does too. Wait until we get to ones where, oh yeah, the fourth one is a little bit more fun. So this one also has the original graph. Analyze it and draw the graphs of f prime and f double prime. And the same thing, I want you to do the next two because they're the same idea. And draw the graphs of f prime and f double prime. We'll go over them in a second. All right, let's check over the first one. So on the first one, we were given the original graph, and we know that there is a maximum, call that point C, or a minimum, at that point C. So first of all, on your derivative graph, you must have your x-intercept there. That's very important, because if you have a minimum, that means the derivative is equal to 0. Again, it might be helpful to draw your number line, mark point C, and your original graph is going down and then up, making that a minimum. So if it's going down and then up, that means on your derivative it had to be negative and then positive. So once I've got that point C, this part has to be negative and this part has to be positive. And we can actually think about this. If you wanted to actually get correct values, for example, at -1, 0, I could, to the best of my ability, draw a tangent line. And once I have that tangent line, that's what your first derivative does. It finds the slope of that tangent line. So I'm going to say, oh, this looks like -2. That would tell me at -1, I would have -1, -2 on my other graph, because that would be the slope at that point. That's the idea of your first derivative. It's just figuring out all the tangents and all their slopes and plotting them. But I find doing the number line really shows that well. Like, all of your tangent lines here are going to be negative. All of your tangent lines here will be positive. That's what shows it decreasing then increasing. And then you would get that straight line. Knowing that this is a parabola means that we should get a linear equation here. And then the derivative of a linear equation should be constant. And with your second derivative, it's always concave up. And if it's always concave up, it means that your constant has to be always positive. Where that is exactly, well, had I picked these 2 points on my derivative and found out its slope was 1, then this might be at 1. But again, we're sort of estimating this because we don't have more numbers. Same thing can happen with this cubic graph. Okay? The original graph has a maximum here and a minimum here. Well, this one's at 0. I'm going to call this point C. It's very important then on our derivative graph that at these 2 points, it's going to be x-intercepts on our derivative graph. If we draw our number line off to the side for a derivative, we would have had the point 0 and the point C on there. And our original graph goes increasing, then decreasing, then increasing, which implies positive, negative, positive. So once I have those two x-intercepts, I know that between 0 and C, it's negative. That's why it's below here. On this side, positive. On this side, positive. We've got a little bit of Mr. Lafrance French happening here. Do you notice it? Then I'm going to call this point D, because now we have a place where our first derivative is equal to 0. That is corresponding to an inflection point on our original graph. So when I draw my number line here for f double prime, and I put in point D, I know that it's changing from concave up and concave down. It's concave down here, and it's concave up here, meaning that it's negative here and positive there. Notice how our green graph is below the x-axis here and above the x-axis there. I find that really helpful for telling, because sometimes you're like, I know I have to draw the line, but you might get confused which way the slope is. In fact, it's very tempting, okay? Can you see yourself getting the point D, being really good, and then being like, ooh, it's decreasing. So since it's decreasing, it's going to be like, yeah, I want to decrease as well, and go in the wrong direction. It's so tempting. So I find drawing that number line and actually going, oh no, it's actually negative there. That's increasing because this is like, otherwise it can get yourself confused. So that number line is very helpful. And again, what does the second derivative tell us? If it's negative, it tells us the first derivative is concave down. If it's negative, it tells us the first derivative, 1 up, is decreasing. So we also have, right, and I've seen this, I've seen this sometimes, Carol. I've seen it done like this sometimes. So we've got the point D on here. They've labeled this as F double prime and put the negative and the positive. Then up here they write F, and in between they write F prime. Because if it's negative, that tells us on F it's concave down and concave up. If it's negative and you just went up one level, it would tell you that F prime goes down and then up. Does that make sense of having all three on one? And that only works with the F double prime. You can't have all three on one using the F prime stuff, because F prime stuff would have 0 and C on it. But this, the plus and negative go to the F prime, the increasing, decreasing, that's really F. So whenever we're drawing those number lines, we're always showing two things. And you can, with the F double prime, actually show three things. Usually we just show the plus or minus in concavity because we're worried about the original graph. But in this case, we could also talk about what's happening on F prime. Is F prime going down and then up? Yes, we can see that as well. These are the most straightforward when they give you the original graph and ask you to draw the derivatives. But in our next example, we have the derivative graph. And so now you have to think, okay, I have the derivative graph. What does this mean? And how could I draw the original graphs? So, the derivative graph was the black one. If we draw our derivative number line, we would know that we would have the points -2, 0, and 3 as critical points, because that's where it's equal to 0. On our derivative graph, can you see that less than -2, the original graph, is positive? Then in between -2 and 0, it's negative. Between 0 and 3, it's positive again. And then after 3, it's negative again. So what does that tell us about f? F has to be increasing, then decreasing, increasing, then decreasing. So at negative 2, we need to have a maximum. At 0, we need to have a minimum. At 3, we need to have another maximum. And there's a little bit of give in this question. Because if I took this same answer, oh, that's not what I wanted. Oh, we'll just ignore the fact that I want to do something and it's not letting. No, wait for it. I took the same answer. Oh, I could move it up. We just have to use our imagination a little bit. Why could I just move it up and have and still get full marks? Well, this original equation in green, if that was our original equation, which is some sort of x to the 4 graph, plus dot, 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 it could have a plus 7 at the end. What would happen to that plus 7 when I did the derivative? It goes to 0. If I change that plus 7 to a plus 70, can you see that that would be a translation and move it way high up? Right? Don't be mean to me and say, well, I did the right graph, but I just translated up 8 million units, so that's why you can't see it on my page. But you should still give me full marks, Mr. JR. That's a good argument, right? So where we have these 3 points doesn't really matter as long as they match up with the x values.
Would it matter if you translated them down?
You could translate it down the same way, right? I could be like, I'm tired of being a positive person. I'm going to change this to negative 70 and then shift it down. Same idea. As long as those maxes and mins are in the right place. So these questions are kind of a little bit annoying because you don't have the right numbers. You would need more information to be able to find out what exactly was that last number in order to graph it. So this is the best we can do. And if you graphed yours and had those in different points, in different places, it would be perfectly fine. But that it should bother you a little bit, like, oh, it's not really completely accurate because I don't have enough information to be completely accurate. And same thing with our last one for today. Now we have the second derivative. And we want to work backwards and find our first derivative and our regular one. So if we look at this and we start with our number line for our second derivative, it will tell us stuff about our first derivative and the original function. Move this down. So our second derivative, I'm going to label this point here as C. That's the only place where our second derivative is 0. Our second derivative is negative on this side of C and positive on this side of C. Normally we just talk about F, so we would already know concave down and concave up. But we can also use this to tell us something 1 up. If I go from F prime up to F, I know that F prime has to go down and then up. And since F double prime is linear, if you went up 1 level, you would get quadratic. Now, I don't know exactly how far down it goes or how far up it goes. The key thing right here is I'm looking for that point. See how on F prime that needs to be a minimum? And I know that F prime needs to be going down and then going up. It could be wider, it could be narrower, I'm not really sure. I'm just getting a basic idea. And it could be shifted up and down. It could have been a parabola way up here. for all we know. Which technically would change how we do the next part. By doing the parabola down here, you see that I made two x-intercepts. And so that forced me to have a maximum and a minimum. If I had drawn my parabola higher up, I might have no maximums and minimums and just have an inflection point. So there's like more than one right answer that looks completely different for this question based on how you decided to draw the quadratic. But if you decided to draw it this way, then at these points you need your max and your min, and you know that it's concave down and concave up, giving you that shape. All right, I'll see you guys tomorrow.